the energy for the reactants. What's the energy for the reactants going to be? Calcium sulfate, negative 1432.7. And sodium hydroxide, negative 426.8. But I have to multiply that one by 2. Is that true? Because I have 2 moles there. Okay. So products minus reactants. Anybody get a value here? Is it D? Negative 84.79. Okay, so does that reaction up there require or release energy? It releases energy. Okay? So, what does this mean? We spent a whole chapter talking about weird kind of energy-associated reactions and recognizing how to identify what the energy associated with the reaction is, right? What does that mean? Well, hopefully that means that when somebody on the internet says, I've created a car that can burn carbon dioxide and move around, right? What do we know fundamentally about that idea? What do we know? Let's see, how much energy does it get to create carbon dioxide? Is that one on here? Negative 74.84. Do you guys see it? Negative 74.84. So if I'm taking carbon dioxide, what kind of products could I make? Am I wrong? Did I see it up there? Am I wrong? It's negative what? Oh, really? No, that's carbon monoxide. Isn't it? I'm on carbon. 1, 2, 3, 4, 5, 6. Okay, negative 393.5. All right, good. Negative 393.5. 393.5. Okay. I need a product over here that contains carbon and oxygen, right? Because I'm not going to change elements. That will release more than the negative 393.5. Right? So another way to say that, I want it to be like a negative 100, right? Because this way, negative 100 minus the negative 395 would be a negative value. Did I do that right? Oh, no. Sorry, it needs to be greater than products minus reactants, right? So let's say I put something in. So this is a negative 393.5. Yeah, products need to be negative 500 minus a negative 393.5. Right? Because then it would be like adding. Oh, so it just needs to be less than 393.5, right? A negative less than 393.5. Because if I'm going products, negative 100, subtract the negative 393.5. Oh no, that's a positive value, right? Negative, that's a positive value. So my car that's going to burn carbon dioxide needs to create a product here that has a value greater than a negative 393.5. All right, let's find it. Something that contains carbon that has a value greater than a negative 393.5. In other words, more negative than a negative 393.5. All right. What do we got up there? Anything? I'm not seeing anything. You guys see anything? Okay. So we're taking carbon dioxide. We're going to do some chemistry on it. And we're going to make something that releases more energy than the negative 393.5. And you'll find that, what? There's nothing out there. There's nothing out there, right? There might be a few crazy little things, and you could try to make some sort of system that utilizes that carbon dioxide. But carbon dioxide is extremely low in energy, right? And to find something even lower in energy would be a very difficult challenge. Okay? So understanding fundamental laws of nature like this can save yourself a lot of time. You don't have to invest in such an idea. You don't have to worry about trying to search for it yourself, right? I mean, unless you can think of a compound or find a compound that can release energy, you don't have to spend any time performing reactions with carbon dioxide that way, right? All right, so there's some fundamental truths there that I think are valuable for you moving forward in your life. So we're going to move on now to chapter 8. And we decided that we're not going to have a test after chapter 7, but we might have one after chapter 8, right? We'll see where we're at. We might be so close to the end that we don't want to do that either. Let me get the slides for chapter 8 here. And while we're handing these out, I'm going to talk to you a little bit about, there's a roll too going around, so there's one of these for you. There you go. Start passing those around. I'm going to start or tell you or talk to you a little bit about models, right? And we've talked about this before, but I want to remind you. Our model for the atom, right, has a nucleus. And what's in the nucleus of our atom? What's in the nucleus of our atom? Protons and neutrons. Very good. So in the nucleus of the atom, we have protons and neutrons. And our model shows the electrons kind of like this, right? And this model, kind of what we call a planetary model, because it looks like the solar system, helps us a lot. And we can answer a lot of questions by this model. However, this model is not correct. It's not how things actually are. And that doesn't mean we don't use the model, but we do want to be aware of how things actually are. All right? And there are other interesting phenomena that are associated with the fact that when things get really small like this, just because we draw a planetary model and it follows certain patterns, just like we would think planets would move in these orbits, we can answer questions with this model. It doesn't mean it's correct. And in general, whenever you're studying something and you know that there's a model, if you make findings that suggest that the model doesn't fit your findings, it doesn't mean you want to throw out the findings. And you don't want to try to fit your findings to the model, right? It's kind of like having an experiment where you know what you want the answer to be, and that can be dangerous and ineffective. So we're going to talk a little bit more about what is really going on between the protons and the electrons. And to do this, we need to talk about light. We need to gather some vocabulary associated with light. Okay? Now, we say light behaves as a wave. All right? It can be transmitted from the sun to the earth. Right? We can transmit light. Now, light is a word that we need to wean ourselves off of, because when we say the word light, we're really talking about a small class or section of a larger, not material, but a larger way of releasing energy. Okay? Light encompasses what we know as ultraviolet radiation, infrared radiation, radio waves, X-ray. All of these are the same type of electromagnetic radiation as what we call light. Okay? So electromagnetic radiation is what we would prefer to say as opposed to light. We can use light, what we know about light, to talk and learn about electromagnetic radiation. We see different wavelengths of light, and we call those colors, right? The range which our eyes can see is, anybody know all the colors in the rainbow? Good, excellent. Red, orange, yellow, green, blue, purple, also known as violet, or indigo, whatever. But violet's a word that I want you to kind of become comfortable using as opposed to purple or whatever, because violet also reminds us that beyond violet, there is another region of electromagnetic energy that our eyes can't see, which is called what? Ultraviolet. On the other side, red, again, red, orange, yellow, green, blue, violet, and then ultraviolet. On the other side of red, there's a range that our eyes can't respond to either, which exists, and is called infrared, right? So we got the infrared, red, orange, yellow, green, blue, violet, and then we got ultraviolet, okay? The range that our eyes can respond to range from 400 to 700, and the units are nanometers. The units are length, because light is described by its wavelength. Okay, so to measure the wavelength, you can go from top to top, bottom to bottom, or from the beginning of one cycle to the end of another cycle, whatever. But that length between there, and in units of meters, nanometers, that's how we describe, as one of the properties, or one of the ways that we describe electromagnetic energy. Okay? So again, our eyes see what range did I say? 400 to 700 nanometers. Okay, so that's the wave's length. X-rays go down to as low as 1 nanometer or less, right? Infrared rays above 700 nanometers, okay? And they can get into the microwave range, right? Microwaves utilize electromagnetic energy that has wavelengths in the region of how big, do you think? Micro what? Micrometers, right? Not nanometers, but micrometers. Does that make sense? Okay. How do microwaves work? The electromagnetic energy in the microwave is tuned to excite what? Have you guys ever? The water, that's right. So what happens, what kinds of things can you put into a microwave and turn it on and then pull it out and it's like it hasn't even heated up? You guys ever done that before? What's that? Have you ever tried to put a piece of really dry toast in the microwave? That won't heat up very well, right? Ceramic things, glass ceramic things, generally won't heat up very well, right? Certain chemicals just won't respond to that wavelength of electromagnetic energy, right? Okay? So, the other parameter is what we call the frequency. The frequency. Frequency simply means how frequent it goes up, or how frequent it passes through one cycle. How frequent. And the units for frequency are per second. So when you say it's 300, you're saying it's 300 per second. Frequency is not limited to wave description, right? We use frequency to describe the effectiveness of our computers, right? How fast they are, right? How fast the hard drive records or rewrites itself. Okay? So we have wavelength and frequency. Now, one thing that we don't talk a whole lot about is the speed of light. Does anybody know the speed of light or electromagnetic energy, which is one and the same? The speed of light? 3 or 2.998 or 2.9979, whatever, times 10 to the 8th meters per second. Okay, that's the speed of light. That's the speed of electromagnetic energy. Radio waves, X-rays, ultraviolet, UV, all these different lengths of electromagnetic energy travels at this speed. Yeah, go ahead. In a vacuum, actually, in a vacuum. And that's right, that if it's going to go through air or water or whatever, then it will have a different speed. But if I have this wavelength or photon of electromagnetic energy and this one, and the question is, here's the starting line, and they have a race across here, which one's going to end? Which one's going to get to the finish line first? Which one has the shorter wavelength? The bottom one has a shorter wavelength. Which one has a higher frequency? Higher frequency. Bottom also, right? How frequently it goes up. It goes up more frequently. But which one's going to get to the other end the fastest? The same, right? The same. Because they both travel at the speed of light, the speed of electromagnetic energy. Okay? So we don't have to worry about light or speed so much, but we can realize that because these are traveling this direction, the same speed, then there will be this relationship between wavelength and how frequently it goes up and down. And that's the relationship. The speed of light equals the wave's length times the frequency. Okay? And this is something that they and you should understand. Let's see if you can figure this out. Answer this question down here. What's the frequency of a radio station if it says it's transmitting at 300 megahertz? 300 megahertz. No, sorry. What's the wavelength? If the frequency is at 300 megahertz, what's the wavelength? Okay? So, we got the equation there. Speed of light equals wavelength times frequency. This is our frequency here. And we want to know what the wavelength of our electromagnetic energy is. Okay? We've got to deal with some prefixes there. We got mega. What is mega again? 10 to the what? 10 to the 6, isn't it? Okay, what do we get? Anybody get it? What'd you get? So what did you put in your calculator? 3 times 10 to the 8th. 300 times 10 to the 6th. Did you convert that to per seconds instead of megahertz? So 300 times 10 to the 6th? Yeah, so the mega is 1 times 10 to the 6th. True? So 300 times 10 to the 6th hertz, which is units per second. All right. What did we get? You had the right answer, but the decimal place in the wrong spot, right? It's a good practice for your calculator. 3 times 10 to the 8th divided by 300 times 10 to the 6th, which is also essentially what? Is that also 3 times 10 to the 8th?
Is it 1 times 10 to the 12th?
No. So we got 3 times 10 to the 8th divided by?
It's 0.9909.
Yes, that's right. It's 1, right? Okay. And you can see our units work out. We're dividing by per seconds here. We're left with meters. Here we're dividing by per second. We're left with meters. Okay. If you use 2.9979 whatever instead of 3, then the answer is 0.999. But otherwise, it's just 1, right? Okay, can you see it? Anybody want to talk about that some more?
What unit is that? What is that?
Meters. We're looking for the wave's length, and the units is meters. Anybody want to talk about it? Did you just put it into your calculator? Okay. You having trouble getting that value out? Okay. Do you know how to write 3 times 10 to the 8th? Does everybody know how to write 3 times 10 to the 8th in their calculator? When you're done, now there's a variety of ways that people like to do it, but when you're done, it should really say 3E8, like that. Can you make it look like that? So you write 3, and then it's like second, and then there's the EE, but can I borrow this for a second? See this comma, the comma. For most calculators, it's that comma there. So you go 3, second, comma, 8. All right? That's what you want to do because that will keep the order of operation straight in the calculator's mind. Okay? And then you'd want to divide by 3 times 10 to the 8th, or you could say 300. Again, times 10 to the second, comma there, and then you put in your exponent.
You put the comma before the E?
The comma makes the E. So you put second comma, and it actually gives you this exponent, which means times 10 to the. So this means 3 times 10 to the, and then you put in the 8. Does that make sense? Oh. What kind of calculator do you have? Is your phone there? Or?
Oh, yeah, no, I got it.
Oh, you did get it. Okay, good. So this is a...
I have one, I just left it at home.
Okay, good. All right. So yeah, you don't want to. You want to bring your calculator so that there's plenty of experience typing in exponents, sort of thing. Okay. Anybody else want to deal with it? Anybody else want help? Trying to get the answer. Did you get the answer or no? Did you get it? Okay, so how fast, when I send a call, beep, 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 and it's going, the information is traveling from here to the satellite back to my wife, how fast does the information travel from my phone? What's that? Very fast? What's the rate at which the information is traveling? It's the speed of light, right? Because what am I sending here? What is this? How do I get information here and back? It's radio waves, right? It's the same stuff. Wi-Fi speaking to us through radio waves, right? We communicate through electromagnetic energy, right? So all this business of sending information wirelessly, right, through the air or whatever, that is the movement of electromagnetic energy and sending information back and forth, okay? Now, that doesn't mean that it's going to happen at the speed of light because it has to run through a computer and all that stuff, right? So there's things that can slow down the process. But I want you to recognize that all our communications all of our wireless communications are occurring through radio waves, which is basically what we're used to calling light, electromagnetic energy. Okay, so here's some other things that are associated with electromagnetic energy. Here's our ultrasound, right? Here's our X-rays over here. Different medical observation techniques. Okay, UV rays, ultraviolet rays cause sunburns, right? Now, another thing that I want to make sure that you understand, and not just for this semester, but for the rest of your life, is the relationship between the colors of light and the wavelengths, okay? So when I say that we can see between 400 and 700 nanometers, I also want you to know whether we can see, or I mean, what we mean when we say 400 and 700 and red and violet, okay? Now, you might know because of something you saw recently, but I want you to remember because of the energy associated with these different colors of photons. Let's see, where is it at? So, this is the relationship between the energy and the frequency, all right? The greater the frequency, the more frequent the line goes up and the wave goes up and down, the greater the energy. The greater the energy. So what is more dangerous to us then? Red light or violet light? Or do we know? Which has more energy, red light or violet light? Which is more dangerous, infrared light or ultraviolet light? Have you ever bought sunglasses that say, these sunglasses will protect you from, what do they say? Do they say infrared? What do they say? They say UV, don't they? Ultraviolet light, okay? Although it sounds like a good business plan to me, make glasses that will protect people from infrared light, right? So, ultraviolet is the dangerous one. So what does that mean about violet's wavelength? Is violet have a higher frequency or lower frequency than red light? Higher. It happens more frequently. Okay, so if we were going to call one of these red and one violet, which one would be our violet? The bottom one. This one would be our red. Is that consistent also with wavelength? Does red have a longer wavelength than violet? Is that what we would expect? If it goes up and down more frequently, does it have a shorter or a longer wavelength? Shorter. Okay, and another way to think about it is X-rays are very short. They say they have more penetrating power. It's not really consistent. I mean, it's consistent, but it's not because they can get through your skin better. But you can think of it as being smaller and being able to sneak through your skin, right? So the relationship between energy and frequency is a direct one. The higher the frequency, the higher the energy. The relationship between energy and wavelength is inverted, right? The longer the wavelength, the lower the energy. Okay, so can we identify what the energy is of a 450 nanometer photon of light? 450 nanometers, how much energy is associated with that photon of light? Well, if we look back at this slide, we'll see this constant here, 6.6 times 10 to the 6th, or 6.626 times 10 to the negative 34, joules of energy for a given photon. This is called Planck's constant. You multiply it by the frequency, and that will give you the energy for our photon of light. So, 450 nanometers. Here's something fun we can put into our calculator, right? 450 nanometers. How does wavelength relate to frequency? How does wavelength relate to frequency? I think I just erased it. How does wavelength relate to frequency?
The shorter the wavelength.
Yes, that's right. Through
Light.
the speed of light, right. So, can you identify what the frequency is given this wavelength? 450 nanometer. And then h, Planck's constant, which is on that previous slide, times the frequency will be the energy associated with that photon of light that has that wavelength. Okay, what was the wavelength that we're after? 450 what? Nanometers.
Is that negative
10 to the minus 9, that's right. So that's a good one. 450 times 10 to the minus 9. Speed of light, what was that? 3 times 10 to the 8th meters per second. That'll give us the frequency. Multiply the frequency times Planck's constant, and that'll give us the energy in joules. B, as in boy. Did anybody try to or find out what the frequency was yet? What's the frequency?
6.66
Times 10 to the 14th. Anybody else get that for the frequency? The only one who solved it. Did anybody else try to get that for the frequency, or did you just move right ahead? So 450 times 10 to the minus 9th. This is 3 times 10 to the minus, or 3 times 10 to the 8th. So 3 times 10 to the 8th divided by 450 times 10 to the 9th, minus 9th. That should be 6.6 times 10 to the 14th. Anybody else get that for us? Why do we have to identify the frequency? Are they asking for the frequency here? No, they're asking for the energy. But why do we have to find the frequency? Yes, that's right. The frequency relates to the energy through Planck's constant here, right? Could somebody else tell me that that's the right frequency? Yeah? No? What'd you get? Okay. So we have our wavelength, right? And from our wavelength, we should be able to identify the frequency. Remember that business or no? Using the what? Speed of light. So if we take the speed of light, type that into your calculator. Everybody type in the speed of light into your calculator. Divide by our wavelength. It has to be in meters, right? It can't be in nanometers. So it's 450 times 10 to the minus 9. Anybody else get 6.6 times 10 to the minus 14? No? What'd you get?
You can't just divide by 450, that's just like you have to do 4 times.
You can't just divide by 450 because this is in units of what? Nanometers. And this is meters per second. So we have to do 450 times 10 to the minus 9. That's now in meters per second. Or sorry, in meters. And then we can get per seconds by dividing the speed of light by this. What's that? Still getting it? Oh, wonderful. Fabulous. Did anybody over here get it? Okay. Let's try it. Let's put it in the calculator. 3 times 10 to the 8th. 3 times 10 to the 8th divided by 450 times 10 to the minus 9. Let's everybody work together. Put this in the calculator. Here, let me see.
I got it now.
Good. Okay, so watch this.
Okay.
3 times 10 to, let's see this little second sign there?
Okay.
8. All right? Divided by 450, and you make it times 10 to the minus 9. Second, this. There you go, and then negative there. Got it? Did you get it? It's not that deep. That's music. Well, the value that's provided this year is, where is that, 450 nanometers. And we need to know what that is, not in nanometers, but in meters, because the speed of light is in meters.
Oh, no, that one, like, what we, that was,
Nanometers is the same as 10 to the minus 9 meters. Are you getting it? Yep. Did you figure it out? You have a calculator? Or, yeah, a little bit. It's crazy. I wonder if we'll ever be able to move away from calculators on our phone. You gotta get a calculator that you can work with in class like this, or in at least in, you gotta bring it to class too, so you can be able to answer these types of questions. So hopefully this has given us the 6.6 times 10 to the minus 14. And that is in units of per second. That's our frequency. Now what do we do with that value? Multiply it by frequency times Planck's constant gives us the energy. 6.626 times 10 to the minus 34. 6.626 times 10 to the minus 34. Okay. Let's see if we were right. It is B. Wonderful. Good job. So the take-home messages are a variety, one of which is there's a direct relationship between which one? Frequency and energy, or wavelength and energy?
Frequency and energy.
Yeah, that's a direct relationship. The more frequent that the wave goes up and down, the more energy it is. Okay? If I lengthen the wavelength, how does that affect the frequency? The longer the wavelength, the what? The frequency. The lower the frequency and the lower the energy. Yeah.
Does it mean that if we have a low frequency, like the light is really strong?
High frequency.
The luminosity is.
So we got 30 seconds here. Well, maybe not, but I'm going to take 30 seconds. That's a very good question, because people were shining light on metal, and they would see that the metals would sometimes release electrons, and they couldn't figure out why that was happening. And they would shine a brighter light, thinking that it would release more electrons, but it wouldn't release much more electrons. It really related to not the brightness of the light, but the color of the light, the energy of the light. We'll talk more about that. It's called the photoelectric effect. Okay, see you guys on Wednesday.